Okay. Otherwise, for those who are like maybe in mainland China right now still, okay. So for those students, yeah, of course they can submit them online through the Moodle system. Okay. So any question? Homework 1. And wait, so how many people have already downloaded homework 1 problems and started solving homework 1 problems? No? That's fine. Yeah, you still have time. Okay. Okay. How come I think there are less students today? Is it because some people dropped the course? Is the class material difficult to understand, or you think it is okay? Yeah, if you have any question, let me know. Okay. So, last time, basically, we have finished like unconstrained optimization using analytical methods. That is, we basically learned how to perform the calculations by hand. Okay. And today, let's continue. Let's continue with this new topic. That is, what if there are constraints? Okay. So, let's start. Let me start over here. So, okay. So classical methods for constraint optimization. Yeah. So we will still try to basically perform the calculations by hand for this kind of problems with constraints. And let's start with equality constraints. Okay. Yeah, I can use this blue one. So. Problems with equality constraints. Okay. Oh, and I believe now we can just directly start to talk about this with multivariables, okay? Because if there's only one variable, it's actually very obvious. Let's just start to do this with. How come? Not very good. So I guess I may need to have new pens during the second hour. Okay. So anyways, yeah, let's start. Multivariable. With equality constraints. Okay, and here is the problem statement. That is, we want to find a set of variables, okay? And usually we put all the variables inside of this column vector, okay? So we want to find this set of variables. Suppose there are n variables. So find that to minimize f of x. Okay, but there are several constraints. Okay. Subject to or such that. So in addition to performing this minimization problem, we also have some constraints. Okay. Do I use I or j? I think either way. Okay, over here let me use j. H sub j of x equals 0. Okay. And there are several constraints. So j from 1 to. On the class notes, did I write from 1 to m or 1 to p? Yeah. Okay, I think either way is fine. Because if there are, I think I would say p, okay, yeah. Oh, and the thing is, hopefully, yeah, or usually, p is less than n, okay? Why? I think I talked about this during the, like 2 weeks ago in our first class. That is because we have n variables, right? And we try to minimize this function subject to the constraints. And if p is equal to n, what does that mean? It means that there are n variables and n equations over here. We can just directly solve for the solution without doing any optimization, right? If p equals n, we can directly solve for x1, x2 up to xn using the equation over here. So it's not an optimization problem, okay? Yep. And if p is larger than n, there must be some problem, okay? There's something wrong. So usually p is less than n, and then we can perform the minimization based on p constraints, okay? Yeah. Okay. And there are several methods for doing this, okay? So let's start with the first one, the easiest one. So this is just the direct substitution method. Okay, yeah, direct substitution. I guess, I believe you can guess what this means, right? And let me just give you an example to illustrate the idea. Wait, is it dark enough? If I use the red color, will it be better? See, okay. So let's see an example. Okay, maybe it's better. Okay. Yeah. So let's say we want to minimize. I'll just use min dot. Okay, you know this means minimize. Okay, so minimize f of x, and let's say there are only two variables. Okay, so I'll just say f of x y. And what is this? F of x y is 1 divided by x y squared. Subject to, okay, hopefully you remember, this means subject to, okay, subject to, okay, or such that, okay, anyways, s dot t dot, subject to the constraint, okay, so over here the constraint is h of x, y equals what, okay. Okay, suppose we have this kind of problem. We want to minimize this. So as you can see, there are two variables and one constraint. Okay, this means that we still need to perform the optimization, right? If there are two constraints, we can directly solve for x and y using the two constraints. So that's not optimization. But right now, there's only one constraint, so it's still an optimization problem. And if you want to have the geometric meaning, it just means that when we try to minimize this function, basically we minimize the function along this circular shape, right? X squared plus y squared equals 1 means that it's on this kind of circular shape. Okay, so we try to minimize the function along this kind of trajectory. Okay, yep. So the so-called direct substitution is very easy because we can just perform substitution, right, from the constraint from h equals 0, we know y squared is equal to x minus s squared, right? Yeah. So, thus, the original problem f now becomes this 1 divided by x, and what is y squared? Y squared is just like that, okay? Great. Yeah. And like originally it's a function of two variables, but now we can just say, we can just call this, originally it's a function of x and y, but now we can just call this, like, let's say it's capital F of x, right? Because now it becomes just a function of x, and then you know how to solve this kind of problem, right? Yeah, it's a single variable problem, and we can just use the necessary condition, right? And then use the sufficient condition to make sure that the point we find is a minimum or maximum, okay? So I think you can do the rest, right? Because it's just a single variable problem, okay? And that's it. If you have the question, really, is this so simple? Yes, if there are not so many variables, yes, especially if there are only two variables, yeah, you can just do this, okay? However, in most cases we have more variables, so maybe this is not a feasible way, okay? So let's directly start introducing, let's start to introduce the second method, okay? The so-called Lagrange multiplier method, okay? Yep, but any question? Yeah, so this is just a very straightforward method. Multiplier. Okay, so, yeah. Okay, so in this method, what we want to do is this. We will define a new function, okay? Define a new function that is the so-called Lagrange function. The Lagrange function, I'll just say func, okay? Define the Lagrange function, L. Let's call this L. Okay, so here's the original problem, okay? And now L is a function of x and lambdas, okay? That is, L is f of x, okay, is the original objective function plus the summation of lambda j h j, okay? J, of course, from 1 to p, because there are p equality constraints. So that's it. And if you prefer the vectors format, we can write this down as f of x plus lambda transpose times h vector, okay? Where this lambda vector is, again, lambda 1, lambda 2, up to lambda sub p, okay? There are p different lambdas. And the so-called h vector is just h1, h2, okay, up to h sub p, okay? There are p constraints. So in vector form, this is what we write, okay? F of x plus lambda transpose h, or you can just simply write it down in this way, using the summation sign, okay? Yep. So we just define the Lagrange function, and then we can start to perform the calculation. Is it? 可以看得到吗？哦，还 OK 吗 ？OK, yeah. Okay, so so this is the so-called Lagrange function, and then what do we do with this? I guess I can just write it down over here, right? Because it might be easier to just do it here. So first we define this Lagrange function, okay? Yeah. So for this method, we define this Lagrange function, and then what do we do? Then we just treat this Lagrange function as our new function without constraints, okay? So we just treat this as a new function, so now it's a function of x1 up to xn and lambda 1 up to lambda p. So it's a function of n plus p variables, and then we try to use the necessary condition to find the point satisfying the necessary conditions. Okay? Yeah. So and then what we do is to use the necessary condition. Use to find the up. Okay. What are the necessary conditions? Yeah, of course, it is okay. I from 1 up to n, right? And partial derivative with respect to lambda j equals 0. J from 1 up to p. Okay. That's it. Okay. So use the necessary conditions. So again, as I said, now we treat L as a function of x and lambda, and we just perform the partial derivative. Yeah, just take the partial derivatives and then set them to become 0, and then solve the equations. And as you can see, now we have n plus p variables, and here we have n plus p equations. So basically, we are able to solve for the solution. Okay. However, you guys know that these are just the necessary conditions. When we find some points, it's not guaranteed that the point is a minimum or maximum or neither. Okay, so we may need to do something else to make sure whether it's a minimum or maximum. Okay. Yeah. Oh, by the way, I hope you can see that when we take the partial derivative with respect to x, you need to perform the partial derivative like over here, okay? So, yeah, on the class notes, I wrote it down in more detail, okay? 好，反正就是当你这边要对 x 做偏微分的时候，其实你要看这里，所以就是等于是把 f 对 x 做偏微分，然后每一个 h 这样合起来，反正每一个 h 都要对 x 做偏微分 ，OK？ 那这边的 OK，and the next one, when we take the partial derivative with respect to lambda, actually what we have is just h, OK？ 可以吗？就是当你对 lambda j 做偏微分，就整个 L 对 lambda j 做偏微分的时候，只会剩下所谓的 h sub j。Anyways, if you are not sure how this works, let me just give you an example. Okay, yeah, basically the same example. Okay, let's see. Yeah. So the same example. Okay. So the same example. Now let's define L. Okay. So L of x. Right now there are. So we have x, y variables, and there is one constraint. Okay. So when we define the L, it is a function of x, y, and lambda. Right. Yeah, there is only one constraint. So only lambda, not lambda 1 up to lambda p. Yeah, actually p equals 1. So, over here we have f of x, y plus lambda times h. What is h? H is that x squared plus y squared minus 1. Okay, let me just directly write down f of xy. F of xy is 1 divided by xy squared. Okay. Yep, that's it. So this is our L, and then yeah, it's very straightforward. We just perform the partial derivative. Yeah, just take the partial derivative with respect to x first. So what do we have? When we take the partial derivative with respect to x, we treat y as a constant. Okay, lambda is also like a constant. So 好，对 x 做偏微分的话，代表把其他的 variable 当成是常数哦，只对 x 做偏微分。Okay, so we have negative 1 divided by x squared, y squared, plus 2 lambda x. Okay, and it becomes 0. Okay, so this is the first equation, and then take the partial derivative with respect to y. We have okay, and take the partial derivative with respect to lambda. So the third one, yeah, when we take partial derivative with respect to lambda, we know what we have is just the constraint. Okay, so take the partial derivative with respect to lambda equals the constraint. Okay, yep, let me check. Let me make sure that this is correct. Oh, wait, I forgot. Yeah, there's negative 2, right? Yep. Yeah, y to the negative 2. So negative 2 divided by y cubed. Okay. Okay, so now we have the 3 equations. So as you can see, 3 equations with 3 unknowns. So basically we are able to solve x, y, and lambda simultaneous, right? Okay. How can we solve this? Do I have to solve this for you guys? Okay, I solved it at home. So let me quickly do this. Okay. Yep. So it becomes 2 x cubed y squared lambda equals 1. Okay, so that's the first equation. Yeah. Okay, and how about the second equation? 2 x y to the 4th power but the 2 can be cancelled out, so I believe that is right. Oh, there's also the lambda. Okay, so x y to the 4th power lambda equals 1. Okay, yep. If you try to look at the first and the second equation, you can actually, let's say this is equation 1 and equation 2. Okay, so I guess I need to erase this part. Okay. Okay, so equation 1 and equation 2 together, what do we have? We can just use equation 1 minus equation 2. Okay, and then I'll just 2x cubed y squared minus x y fourth equals 0. Okay, and actually the x can be brought outside, right? So x, so here is x, and y's can be brought outside. Okay, so y squared. Yeah. So I believe this is what we have, right? Let me check again. Yeah, x y squared times 2x squared minus y. Okay, yep, that's right. Okay. So, yep. And I guess I will just okay. And from here we know it is possible that x can be 0, right? Right? Or y can be 0, but this is not good. Why not? Because you see the problem is 1 divided by xy squared. If x equals 0, then it's infinity. It's not good, right? If y equals 0, it's also infinity, so not good. Okay, so and if lambda equals 0, then it's like there's no constraint. It's still not good. So let's just use this final one. Okay, so actually we have 2x squared equals y squared. Okay, so from this we know x is like that, plus minus square root 2 here. Okay. Oh, wait, that's y. Yep. And let's say here is equation 3. Okay. So let's substitute into equation 3. Okay, and finally, equation 3 can become something like this. Yeah. Wait, actually I think we can just directly perform the substitution, because equation 3 can be just like this: x squared plus, what is y squared? Y squared is just 2x squared, okay, minus 1 equals 0. Okay, great. And then x can be solved. Okay, so x is like that, and y, yeah, of course you can calculate y directly. Okay, and that's it. Yep. So when you have x, then you can have y, and of course you can also calculate lambda. Okay, and that's it. Yep. I hope this is all right. And maybe you want to say, I still think the first method is better. Okay, but again, if you want to solve a problem with several variables, like with more than 3 variables, then this method is a more systematic way. Okay, so this is the so-called Lagrange multiplier method. And one more time, what do? We just define the so-called Lagrange function. The Lagrange function is the original objective function plus the summation of lambda j hj, okay, depending on the number of equality constraints you have. Okay, so you just sum all of them together, lambda 1 h1 plus lambda 2 h2. Okay, so after having this Lagrange function, you just treat this new function as your new objective function. So now it becomes a function of lambda, a function of xi's and lambda j's. Okay, and then you perform this kind of you take partial derivatives and set them to be 0, and then try to solve for the point satisfying those conditions. Okay. Yeah. Okay. So, any question? Oh, but over here, when we found the point, it's not guaranteed that it is a local minimum or a local maximum. You need to perform some other calculations to guarantee that. But the good news is, if the functions are convex, then whenever you have some points, whenever you find the points satisfying the necessary conditions, then those points are the local minimum points. Okay? Yeah. But if not, then you need to perform some other calculations to make sure. There is the standard way or the strict way to make sure whether the point you find is a local minimum or local maximum. But there's also another easier way. Okay, not very strict, but